So in this video we are going to discuss the question which appeared in JRF Physical Science examination in December 2017. So let's continue with the first question. The statement is the dispersion relation of a gas of spin half fermions in two dimensions is given by this relationship, where E is the energy and K is the B vector and V is the constant with the dimension of velocity. If the Fermi energy at zero temperature is given to be EF, then the number of particles per unit area is how much? Okay, so we have to find the number density, where number density refers to number of particles per unit area. Okay, so let's continue with the problem. So for two-dimensional system, the density of states in the energy interval. So for a 2D system, the density of states in the energy range from E to E plus dE. So this expression you need to remember, and it is given by, or it's denoted by G E dE, and this is basically equal to G, where G refers to a degeneracy factor, and then area divided by H square and then 2 pi P dP. Okay, let's call this as equation 1. Okay, now here G, it's a degeneracy factor, and this is equal to 2s plus 1, and for the fermion, because s can take value of 1 by 2, so 2 multiplied by 1 by 2 plus 1, and this degeneracy factor, this is equal to 2. Okay, so it's also referred as spin degeneracy, and A is the area. Okay, now the dispersion relationship is given to be, the dispersion relation is given to us E, that is equal to H cut V and then mod of K. Okay, and this can be rewritten as V and H cut K, that will give you P basically. Okay, that's a momentum basically. Why? Because P is equal to H cut K. Okay, so let's call this as equation 2. Okay, so from equation 2, what we notice, P, that is equal to E divided by V. This implies dP, that is equal to dE by V. Okay, now so the number of particles is given by, total number of particles in the system is given by, if we denote the total number of particles by N, that is equal to the integration from 0 to EF. Okay, and then the probability distribution function for the fermion, which is Fe. Okay, and then multiply by the density of states GE dE. Okay, so here Fe, that is the probability distribution function, and this is equal to Fe, this is equal to 1 for all energy less than equal to EF at t is equal to 0, and this is equal to 0 for E greater than EF. Okay, so now because we are doing this integration from 0 to EF, so that's why we can put its value equal to unity. Okay, so that's what we are going to do in the next step. Okay, so the number of particles in the system, that is equal to 0 to EF. Okay, because at absolute 0 all the energy states below the Fermi level, they will be occupied. Okay, so we need not worry about the states above the Fermi level. Okay, so then the value of the Fermi direct distribution function, which is 1. Okay, and then multiply by the density of states, which is given by expression 1 here. Okay, so and G is equal to 2, so 1 multiply by 2A upon H square and then 2 pi p dp. Okay, now this is further equal to 2, I am taking outside, okay, and then 0 to infinity 2 pi a upon h square, 2 pi a upon h square, and then what is p? P is equal to e by v. Okay, so we are substituting the value of p, that's e by v, and then dp, that is de by b. Okay, and this after the integration, this turns out to be equal to 2 multiply by 2 pi a upon h square, and then v square, and multiply by ef square by 2. So this ef square by 2 we will obtain after integration. So sorry, here the limit of integration, it's up to ef. Okay, so some of the terms will cancel. So here we are having h square upon 2 pi. So, okay, so we are going to multiply by 2 pi in the both in the numerator and denominator, and so that we obtain from this equation, I am bringing a on the left hand side. So n by a, that is equal to ef square divided by 2 pi h cut square. So this, because h cut, that is equal to h upon 2 pi. So h cut square, here we have multiplied by 2 pi in the numerator as well as in the denominator. Okay, so and then multiply by v square. Okay, so which is nothing but number density in 2 dimension. Okay, so this is our final answer. So if you just take a look at the option which are given to us, so D represents the answer that we have obtained, ef square upon 2 pi b square h cut square. So therefore D is the correct option here. Now let's continue with the next question. The statement is the relationship between the internal energy U, entropy, temperature, pressure, volume and chemical potential mu, and the number of particle n of a thermodynamic system is given by this relationship. Okay, it's a very simple question. So basically what we need to learn here is that how we get the Maxwell relations for the given thermodynamic potential. Okay, so here the thermodynamic potential that is given to us, it is du, that is equal to TdS minus PdV plus mu dN. Okay, let's call this as equation 1 here. Okay, so here we will call this the S, V and N. We call these as natural variables. For U. Okay, and whereas T, P and mu, T, P and mu, these are the redundant variables, basically redundant variables. Okay, so here because S, V and N, these are the natural variables for U, so what I can do is I can write U to be a function of natural variables which are S, V and N. Okay, so that's an important point to note here. Okay, so now at the same time it's also given to us that U is given to be an exact differential. Okay, so we will make use of this point in developing the Maxwell relationship. Okay, so here we will take only two variables at a time, and then we will try to find out the corresponding Maxwell relationship, and if it matches with the one of the option which are given to us, then we will stop at that point. Okay, so let's first of all we take the first two variables as the we will write U to be a function of U, S and V only. Okay, so further we will make use of the fact that this U, it's an exact differential. So that means we can write that if you take the differential of the internal energy with respect to S and V, then the change of the order doesn't influence the final result. So now because U is an exact differential, so this implies that curly S of du by dv, okay, du by dv by keeping S constant, and when it is with respect to entropy, then it's the constant of volume, okay. Then this should be equal to, if it's an exact differential, then order of differentiation doesn't matter, okay. So curly v of du by ds, okay, by keeping v constant and then by keeping S constant, okay. So let's call this as equation 2. Now from equation 1, what we can learn from equation 1, that t can be written as, from equation 1 implies that t is equal to du by ds by keeping volume and number constant, so by keeping n and v constant. So when these are constants, so these quantities will be 0, and simply we will have du is equal to tds, okay. So that means t is equal to du by ds, okay. Similarly, we can write for the other redundant variables, that pressure can be written as du by dv with negative sign by keeping other two variables constant, that is by keeping s and n constant, okay. And the third variable is mu, so mu can be written as, it's du by dn by keeping s and v constant, okay. So now here, because we need du by dv, so du by dv is given by this expression, so it's minus p. So here these three results together with equation 2, they gives us curly s of du by dv at constant s, okay. So du by dv, so that's minus p basically, okay. So that means minus dp by ds minus dp by ds, and keeping the other two variables constant, that is n and v, and that will be equal to curly v of du by ds. So du by ds is t, okay. So dt by dv, and by keeping s and n constant, okay. So if you just take a look at the option A here, so which is minus dp by ds at fixed nv, that is equal to dt by dv, this one. So that means A is the correct one. Now let's continue with the next question then. So it's the number of microstates they are given to us for the n particle, okay. So we have to find the PV, its pressure P, okay, we have to find basically the equation of state for the given system, okay. So let's see how we can handle this problem. So what we are given is the number of microstates which are accessible to the given system, they are given by omega, and that is equal to V minus NV power n, okay, and AU upon n power 3n by 2, okay. And A and V, they are given to be positive constant, its pressure, volume and T, they are related by, okay. So that means basically we are supposed to find out the equation of state, okay. So let's call this as equation 1, okay. Now the entropy, it's given as S is equal to K B ln omega, okay. And if you just plug in the value of omega here, so we obtain Kb, so the Kb and then logarithmic of this quantity, okay. So that will give you nkb ln b minus nb, and then the second term, okay. So this will come in the beginning while taking logarithmic and multiply by k. So this is equal to basically 3 by 2 nkb ln au by n. So that's the expression for the entropy, okay. Now we will make use of the first law of thermodynamics, which is du, that is equal to TdS minus PdV plus mu dN. Let's call this as equation 3. Okay, so from here, from this equation we can write P that is equal to minus du by dV by keeping S and N constant. Okay, and T can be written as T by keeping B and N constant, so that they will be 0 in that case. So T will be du by ds, du by ds by keeping N and V constant. Similarly, mu that is equal to du by dN by keeping S and V constant. Okay, and from here, from this result, what I can do is I can write 1 by T that is equal to ds by du by keeping N and V constant. Okay, so here I'm going to multiply P with 1 by T. Okay, so these two results, this one and this one, so they give P multiplied by 1 by T. Okay, that is equal to P multiply 1 by T. Okay, so I'm bringing 1 by T at the first place, so which is ds by du at N and V constant, and then multiply by P, which is minus du by dV. So I'm bringing minus sign here and multiply by du by dV at S and N. Okay, so here I can write this as this. We will make use of the reciprocity theorem here, so negative sign will disappear. So this is equal to basically ds by dV by keeping N and U constant. Okay, so here we have made use of the result which we call as the reciprocity theorem, which says that if we are having 3 variable, then in that case dx by dy by keeping z constant, this is equal to minus dx by dz by keeping y constant, and then dz by dy by keeping x constant. So here we have made use of this result, and this is known as the reciprocity theorem. Okay, so now we have a important results with us which says that P by T that is equal to ds by dV by keeping N and U constant. So here we will make use of this result. Let's call this as equation 4. Okay, so we will make use of equation 2 and equation 4, and then we will write that P by T that is equal to ds by dV. So we will differentiate this equation 2 with respect to volume. Okay, so here there is no volume term in the second term here, so its differential with respect to volume, that will become 0. So we only need to worry about the first part. Okay, so P by T that is equal to curly V of curly. Okay, I'm not writing curly V, so I'm directly differentiating it. So NKV, and then differential of the logarithmic term, that will give you divided by V minus NV, and then differential of V, so that will give us unity. Okay, so after rearranging these terms, we obtain P into V minus NV that is equal to N KVT. Okay, so that's our final result. So let's see which option matches. Oh, okay, it's D. Okay, so D is the correct one here. So let's take a look at the next problem. The statement is a closed system having 3 non-degenerate energy levels with energy E equal to 0 plus minus E is at temperature T. For E is equal to 2 kT, the probability of finding a system in the state with energy E is equal to 0 is. Okay, so let's try to understand this problem. So we are given a system with 3 energy levels. Okay, so let's first draw the energy levels, and these are minus E, 0 and plus E, and it's also given that all of these energy level, they are non-degenerate, so that means degeneracy for all the level, this is unity. Okay, now we can write the partition function for this system Z, that is equal to sum over all states Gi exponential minus beta EI, okay, where GI is the degeneracy, which is unity in this particular case. Okay, so this is equal to now for the first energy level, which is having energy minus E, the terms are G, it's 1 for the all cases, so therefore exponential beta E, the first term, plus exponential beta multiplied by 0, so that will give us the unity, plus exponential minus beta E, or this can be rewritten as 1 plus exponential beta E plus exponential minus beta E. Okay, or in simple words, this is equal to 1 plus 2 cos hyperbolic beta E. So this is basically 2 cos hyperbolic beta E. So this is our partition function. Okay, now we want to find the probability that the energy states with E equal to 0 is occupied. So that probability is given by probability that E is equal to 0 is occupied, that is equal to exponential minus beta multiplied by the energy divided by the the partition function Gi exponential minus beta EI, and that is equal to 1 divided by 1 plus 2 cos hyperbolic beta E. Now we are given a condition that we have to find the probability for this particular value of beta E. So we are given that E upon KT, that is equal to 2, which implies beta E is equal to 2. Okay, so that means the corresponding probability E equal to 0, that is equal to 1 divided by 1 plus 2 cos hyperbolic, it's beta E, that's 2, so 2 cos hyperbolic 2. Okay, so that's our answer. So therefore it's A, option A is the correct one. So let's continue with the next question. So we are given a situation where two non-degenerate energy level with energy 0 and E. So we are given a system with two energy level whose energies are 0 and E, and these are non-degenerate. So that means G value for these two levels, that is equal to unity. Okay, and these are occupied by n non-interacting particles. Okay, so we are having a system of n non-interacting particle at temperature T. Using classical statistics, the average internal energy of the system is, okay, so this can we can work out the average energy by making use of the partition function approach. So first of all we will write the partition function for this n particle system, and that is equal to exponential okay, so I'm writing directly the partition function for n particle system, that will be simply z1 power n. Okay, so what is z1 now? Z1 is the partition function for a single object, so that is exponential, as we did in the previous problem. So G exponential minus beta EI. So here we will have only two terms, one corresponding to E is equal to 0, and then exponential minus beta E corresponding to the second energy level. So therefore Zn will be 1 plus exponential minus beta E power n. Okay, let's call this as equation 1. Now the internal energy, that is equal to minus curly beta of ln Zn, and that is nothing but, if you take the logarithmic of this function, then this turns out to be equal to minus n curly beta of 1 ln 1 plus exponential minus beta E. So n, because actually it was a 1 plus exponential minus beta E power n here, so I took n before the differential because it's a constant quantity. Okay, now we have to simply differentiate this expression with respect to beta, and that will be our final answer. So u will be minus n upon 1 plus exponential minus beta E, and then differential of exponential minus beta E, and then multiply by minus E. Okay, and this is equal to n E exponential minus beta E upon 1 plus exponential minus beta E. Now if we multiply both numerator and denominator with exponential beta E, so we are left with n E upon exponential beta E plus 1. Okay, so therefore A is the correct option here. So let's continue with the next question. The statement is, consider a quantum system of non-interacting boson in contact with the particle path. Okay, the probability of finding no particle. So the probability of finding no particle in a given single particle quantum state is 10 power minus 6. So we are given a probability of not finding a particle in a given quantum state. Okay, the average number of particle in that state is of the order of, okay, so here we are going to make use of the fact that the average number of particle, the average number of particles in a particular state, this is basically proportional to the probability. Okay, so that means if somehow we are able to find out the probability, so the average number of particle will be proportional to that particular number. Okay, so here we will assume that let f OC, that is the probability of occupants. Okay, so we will call this as probability of occupants. Okay, or you can say that which is proportional to the average number of particle in a state, average number of particles in a state. Okay, now so same way we can define the f, the probability of unoccupancy, and this is equal to probability of unoccupancy. Okay, and that is equal to the probability of finding no particle. Unoccupancy means no particle is there, no particle in a given quantum state, in a given quantum state. Okay, now it's given to us that the f, this quantity, the probability of unoccupancy, it is given to us, probability of unoccupancy. Okay, this is given to us, this is 10 power minus 6. Okay, now we will make use of the fact that the sum of these two quantities, that is probability of occupancy and probability of unoccupancy, this is equal to unity. Okay, so one of the term is given to us, so that means from here we can find the probability of occupancy, that is equal to 1 minus probability of unoccupancy. Okay, and that is equal to 1 minus 10 power minus 6, and this is basically equal to 1 minus 1 upon 10 power 6. Okay, so after solving we will obtain that 10 power 6 minus 1 upon 10 power 6. Okay, so therefore the order of average number of particle, so therefore order of average number of particles, so this is basically number of particle in a state is basically equal to 10 power 6 minus 1. It's basically a numerator basically, and the if you just recall how the probability is defined, the probability that is exponential minus beta e, and then in the denominator we have the partition function. Okay, it's over the all states. So this basically this factor, it refers to the the situation in a particular energy level. Okay, so therefore that's why we are talking about the numerator here. Okay, so that means this is of the order of 10 power 6. Okay, so therefore option B is correct here. Let's take a look at the next problem. The statement is, consider a system of particles which interact by a pair potential which is given by V, that is equal to A r power 6, where r is the interparticle separation and A it's greater than 0, it's a constant, if a system of such particle has reached the Virial equilibrium. Okay, so that means the hint is given in the statement of the problem, so that we can make use of the Virial theorem to solve this problem. The ratio of the kinetic energy to the total energy of the system is, okay, so we have to find the ratio between the kinetic energy and the total energy. Okay, so we will make use of the result of the Virial theorem. So here the kinetic energy, the average of the kinetic energy, okay, which is kinetic energy basically, that is equal to n by 2 and the average of the potential energy. Okay, so this is the potential energy basically. And what is n here? So the n is it's from known from the given potential. So n is here the exponent, which is 6 here. Okay, so therefore the average of the kinetic energy, that is equal to 6 by 2 the average of the potential energy, which is equal to 3 times B. Okay, now the total energy of the system is given by, so let's call this as equation 1, and this is our standard result, and this is equation 3. Okay, now the total energy of the system is given by, of the system is, it is a sum of the kinetic energy and sum of the potential energy, T plus B. So this is equal to 3 times V plus average of V, and that is equal to 4 times the potential energy. Okay, so this is equation number 4. Okay, now therefore the ratio of the kinetic energy, so we are asked the ratio of kinetic energy, that is T to the total energy, that is E. So kinetic energy is equal to T, that is equal to 3 times B. Okay, so that is equal to 3 times B and divided by the total energy, that is equal to 4 times B, 4 times average potential energy. So therefore these two terms will cancel with each other, so this is equal to 3 by 4. Okay, so therefore C is the correct option here. So the last problem in this video, it's from the thermodynamics. The statement is, a monatomic gas of volume V is in equilibrium in a uniform vertical cylinder. Okay, so the lower end of which is closed by a rigid wall, and the lower end is closed by a rigid wall and the other by a frictionless piston. So let's draw the situation first, and then so we are having a gas which is confined in a cylinder. Okay, so we are having a situation something like this. So we are having a cylinder and a gas is confined within this. Okay, so this is our piston here. So let's say this is the initial equilibrium situation. So this is the handle basically. Okay, so here let's say its volume is V. Okay, now this is a rigid wall. In the base it's a rigid wall, and this is the piston basically. The piston is pressed slightly and released. So when the piston is pressed, let's say in the lower direction, and when it's released, so basically it will execute some sort of oscillations. Okay, and then assume that the gas is a poor conductor. It's also given to us that the gas which is inside this chamber, that is a poor conductor. Okay, so that means adiabatic condition, so that means dq is equal to 0. So these conditions will prevail inside the chamber. It's a poor conductor of heat, and the cylinder and piston are perfectly insulating. Okay, so it's further given that this cylinder and the piston, they are perfectly insulated. So that means this relationship, it's valid. Okay, if the cross-sectional area of the cylinder is A, okay, that's given. So its cross-sectional area, this is given to be A. The angular frequency of small oscillation of the piston about the point of equilibrium. So we have to find with what frequency the piston, it will oscillate. Okay, so now let's move step by step. So with this information that the piston and the cylinder, it's insulating and dq is equal to 0, and when the piston, it's pressed slightly, and then it will move in the vertical direction, both downward and upward. Okay, so that means it will execute some sort of oscillation in this direction. Okay, so because it's going to be an adiabatic type of process, so that means here PV power gamma, that will be valid. PV power gamma that's equal to constant, this is going to be valid. And we are given that it's a gas is what kind of monatomic gas. Okay, so that means we will need this information at a later stage. So gamma for the monatomic gas, you need to remember this 5/3. Okay, so now because PV power gamma, it's going to be constant, so that means, so let me call this as equation 2. So from equation 2, what I can do is I can write differential of PV power gamma, that is equal to 0. Okay, so from here I can write dp, and keeping b power gamma constant, constant. Now differentiate to b power gamma and keep pressure constant. So we will have gamma p b power gamma minus 1 dv, and that is equal to 0. And after rearranging this result, we will obtain that dp, that is equal to minus gamma p. So we will take this to the right hand side. So gamma p divided by v, from here v and then dv. Okay, or this can be further rewritten as, because dv is basically equal to what? So when this piston, it's pressed in the downward direction, let's say it's moved by a small distance dx. Okay, so let's try to understand from here. This is the piston, this is the, suppose the initial equilibrium situation. Now suppose the piston is moved in the downward direction by a small amount dx. Okay, so because the cross section area is a, so therefore the small change in volume dv by moving the piston in the downward direction, that is equal to area, the cross section area, multiplied by dx. Okay, so we can replace dv with a dx. Okay, so that is equal to minus gamma p upon b and multiply by a dx. Okay, let's call this as equation 3. Okay, now when piston it is in equilibrium. Okay, so that means when there is no force applied on the piston, so that means when it is in equilibrium, so then its weight basically, which is acting in the downward direction, the weight of the piston, it's acting in the downward direction, mg, this weight will be exactly balanced by the force which is exerted by the gas molecule inside the chamber. Okay, and that force is equal to basically the pressure exerted by the gas molecule multiplied by the cross sectional area. So that means in equilibrium, what we can do is we can write here like this. So in equilibrium, we can write the weight of the piston, that is equal to basically the force exerted by the gas from in the upper direction. Okay, which is nothing but that is equal to pressure exerted by the gas multiplied by the cross sectional area. Okay, so now but this is valid in the equilibrium situation. Okay, but if we want to change the position of the piston by a slight amount dx, okay, as I said here, now if we want to push the piston in the downward direction, okay, so that means the additional force that must be applied, that is given by df, that is equal to a times dp, the excess pressure, dp, that's the excess pressure in excess of p. Okay, so only then we will be able to press the piston in the downward direction, and then once it is released, then it will execute the oscillation. Okay, so here we will substitute the value of dp from equation 3 here. Okay, if you do that, so this is equal to a times minus gamma p upon b a times dx. Okay, and this is nothing but this is equal to, after rearranging all these terms, so this is minus gamma a mg, because p into a, so I am replacing this p into a with mg from here. Okay, gamma a mg divided by b and dx. Okay, now from this equation we can obtain the final results. So integrating assuming that x changing from 0 to a final value of x. Okay, so actually we assumed a change of dx. Okay, if we consider this equilibrium situation to be 0, Okay, so then if depending on by how much amount we have pressed and let the final displacement is x. Okay, so this way we can integrate this equation, and after integration we obtain from this equation f that is equal to minus gamma a mg by v, and x. After integration we will obtain x from 0 to x, that will give us simply x. Okay, and this can be written as this is equal to minus k times x, where k is equal to, let me go to the next slide, where k is equal to m omega square. So basically we are comparing this with the equation of motion of the oscillator. So k is equal to omega square, and that is equal to mg gamma a divided by b. Okay, so from here m and m they will cancel with each other, so we obtain that omega that is equal to gamma time g a by b. Okay, now for gamma value for the monatomic gas, this is 5 by 3, so this is equal to 5 ga by 3v. So therefore our this is our final answer. So let me check which option is the correct one. So this is option A basically. Okay, so 5 ga by 3v.